Hello students, welcome to this session. Here we are going to discuss about the pulse triggered flip-flops. So in the last session we have done discussion on the latches. Now we will move on to the flip-flops. Okay, so in order to discuss about the flip-flops, two things are very important. That is triggering the flip-flops. Triggering is in order to make the device active. So there are two types of triggering. So the first one, it is called as level triggering. Then we have the other type as edge triggering. First, let us see what is the meaning of level triggering. In a level triggering, the output state is allowed to change according to the inputs when the active level is maintained at the enable input. Okay, so if it is positive means then it is positive level trigger. If it is at 0 means then it is called as the negative level triggering. Okay, so in level triggering what happens is output state is allowed to change according to the input. So whenever particular level is maintained at the enable input, actually this type of triggering is done for the latches. Okay, because latches are the level triggered devices. Flip-flops are edge triggered devices. So okay, there are two types of level triggering. First, let us see the positive level triggering. So actually we are telling it as the enable input because this type of input is given to the latches. So this is called as positive level triggering. So in positive level triggering, what happens is the enable input is maintained at the logic level 1. So during this time, whatever the input that is given, according to the input, when enable is equal to 1, we are going to get the output. Okay, so that is latch is enabled. So our latch, it is made active when level of the input it is high. This is called as positive level triggering. Okay, that means latch will respond to the input, okay, only when the enable input is 1 or it is high. Okay, so this kind of triggering, it is called as positive level triggering. Now we'll move on to the next one, which is called as the negative level triggering. So output of the latch, it will respond to the input only when the enable input is 0 or it is low. So that is being shown over here. So this kind of triggering is given to the latches. So here we have the level as 0. That means it is logic level 0. So during this time, the output will change according to the input. When the enable signal is 0, that means at that time latch is triggered or it is latch is made active and output is going to change according to the input that is given. Okay, so this is called as the level triggering. This is negative level triggering. So these kind of triggerings, they are used for latches because latches are level triggered devices. Okay, now let us move on in order to see the edge triggering. So in edge triggering, the output is going to respond to the changes in the input only during positive or negative edge of the clock pulse. So at the clock, we are going to give certain input, which is called as the clock input. So during this, what happens is whenever the clock goes from 0 to 1, that edge, it is going called as positive edge. And the clock, when it goes from high level to low level, it is called as negative edge of the clock. So if the device is triggered during these times, then it is called as edge triggering. So there are two types of triggering. Edge triggering, again it is positive edge triggering or it is negative edge triggering. So this positive edge triggering or negative edge triggering, this kind of triggering is given to the flip-flops. Okay, so that is the main difference between the latches as well as the flip-flops. Actually, there is not much difference between these two devices, but the thing is, they are going to store information, and together we are calling it as a register. That means many latches together or many flip-flops which have been designed one after the other, they will form a register. So a register is nothing but a group of flip-flops wherein you can store certain information. So here what happens is in order to build memories, we are going to use these latches as well as the, right? Okay, now let us see the positive edge triggering. So here what happens is output is going to respond to the changes in the input only during the positive edge of the clock input. So what is the positive edge of the clock input? So that is being shown over here. This is called as the positive edge of the clock input. Here this is also known as the positive edge of the clock input. So if the flip-flop changes its output according to the input that is given during these times, then that kind of triggering it is called as positive edge triggering. So clock is active, that means during this time only the flip-flops are going to be active. Okay, so this is called as the positive edge triggering. Now let us move on in order to see what is the meaning of negative edge triggering. Here the output will respond to the input. So if there is any change in the input, so it will respond to this only during the negative edge of the clock input. So what is this negative edge of the clock input is? This is called as the negative edge of the clock input. That means when the clock goes from high level to the low level, this is called as the negative edge of the clock. So if our circuit, if it is going to respond to the input only during these times, then it is called as negative edge triggering. So actually this kind of triggering is given to the flip-flops, and level triggering is given to the latches. They both are storage devices only, but there is slight difference between latch and flip-flop. Latches will work for the enable signal, and they will have sometimes synchronous inputs, but here in flip-flops they are synchronous with the clock. Okay, so they may be negative edge triggered flip-flops or it is positive edge triggered flip-flops. So flip-flops are the edge triggered devices, but latches are the level triggered devices. These are the main difference between the latches and the flip-flop. So in order to make them active, we need to have to trigger them. So for triggering, there are two types of triggering. One is level triggering and edge triggering. Level triggering is given to the latches. Edge triggering is given to the flip-flops. Right? Okay, now we'll move on in order to see the, now our discussion starts for the flip-flops. Okay, till now we have seen latches. So now let us move on in order to see the flip-flops. Okay, so how a flip-flop is constructed? See, flip-flop can be constructed using NAND gates as well as the NOR gates. But here, as I have already told in the previous sessions, that we are discussing the flip-flops with respect to NAND gates. That's why make sure that you are familiar with the NAND gate truth table. Here we have this, there are two NAND gates over here. Okay, so you could see that these two NAND gates over here, which are cross coupled. Okay, so there are cross coupled NAND gates over here. So this is nothing but our S bar R bar latch it is. This is a latch that is. So to the latch, we have two more gates that are used. So out of two gates, we have to one of the gates we have connected the input S, and the other input, it is nothing but clock. Okay, so now down we have one more NAND gate. To that NAND gate we have connected R. This is one more input. So the other input for this down NAND gate, it comes from the edge detector circuit. So in turn it is clock signal. So thereby our SR flip-flop, it is constructed using the NAND gates like this. We can construct the flip-flop using NOR gate also. This is just an example in order to show how a flip-flop is constructed. So this is a diagram of a SR flip-flop with the NAND gates. So initially we have two NAND gates over here. So to these two NAND gates, there are two inputs which are called as the S input and the R input. These are the inputs that we are giving. The other input being it comes from the edge detector circuit. As I told, these flip-flops, they are edge triggered devices. Many a times I have already repeated this one. Flip-flops are edge triggered devices. So this edge detecting circuit becomes important. So clock is given through this edge detector circuit. So thereby it goes to both the NAND gates over here. Alright. So this is the clock that is being given, but you must note that clock will not be given to the latches. Clock signal is given only to the flip-flops. You will have enable input. So even if it is gated latches, then only you will have enable input. Otherwise, it will have just latches will have here only we have a latch. Okay, so this is a latch that is being shown over here, which is S bar R bar latch. You could see that there is no clock signal that is connected over here. So this is the main difference between the flip-flop as well as the latch. So flip-flop, in order to construct it, we require a latch. Okay, but we'll have additional NAND gates. To these additional NAND gates, we are giving the clock signal. Thereby, we are converting a latch into a flip-flop. Right? Okay, this is how we are going to construct. Okay, first thing over here is we are not discussing in depth of this SR flip-flop. But the thing is, why we are not discussing is because we have already discussed enough about S bar R bar latch. So if you are familiar with this S bar R bar latch, you can easily understand this SR flip-flop. Okay, so in order to understand this SR flip-flop, very important thing is it is nothing but the S bar R bar latch. So once we give the inputs S and R over here, once it is passed through the NAND gate, you could see that you are getting certain outputs over here. Obviously, this is a NAND gate over here. So you will get the complement of this one. Right, see for example, if you are giving 0 over here, right, so if it is 1, okay, what does our NAND gate truth table say? Okay, if any one of the input is 0, what happened to the output? Output becomes 1. For example, if you have connected over here 1, okay, so and here also if you get 1 over here, then what happens if both the inputs are 1? Then your R bar will become 0. What happened here, what you could observe, if S is 0, output of this NAND gate will be 1. If R is 1, the output of NAND gate is 0. That means what? We are getting complement of the inputs. Hope you have understood the meaning of this one. Obviously, our flip-flop is active only when clock signal is given. So there is compulsory input 1 has to be given over here. Is it not? Compulsorily 1 has to be given. So thereby, if we give S as 0, then according to NAND gate truth table, so I think you are all familiar with the NAND gate truth table. So in NAND gate, what happens is if any one of the input is 0, the output is 1. So here S is 0, thereby we are getting the output of NAND gate, this NAND gate as 1. Right? Here we have, let us take, this is just an example how we are getting this complement. For that I have given all these things. So if R is 1, then what happens is here always clock has to be 1, then only our flip-flop is going to function, right? Otherwise we say that flip-flop it is not functioning. So thereby here, that's why I have made it uh, clear over here, it should be 1. So if both of them are 1, obviously we'll get according to NAND gate truth table, if the inputs are same, output should be 0. So that means what? S is here, what you have got, what you have connected S as 0, but you have got here as 1. Since here R is 1, what is the output of this gate? We have got it as 0. That means what? If you pass your S and R inputs to the NAND gate, we are going to get the complement. Okay, so that's why here we have represented it as S bar, here we have represented it as R bar. Okay, so now we are not going in depth of this one, just we are looking at S bar R bar latch, because we have already discussed enough about this S bar R bar latch. So in order to understand this one, now let us just, we'll have a recap of this S bar R bar latch. Just we'll see once and then we'll move on in order to discuss more about the S bar SR flip flop. Okay, so here is the S bar R bar latch. Okay, so this is our S bar R bar latch. Okay, so how it is constructed? It is constructed using the cross-coupled NAND gates over here. You could see that S bar, here we have Q, here we have R bar, and it is Q bar. Now let us see this one. Okay, so now let us see the truth table. See, for S bar R bar, when the input is both 0, 0, we'll get the indeterminate state. When S bar is 0, we are getting, okay, so this is cross asterisk, we call it as an asterisk. That means it is an invalid state. When S bar is 0, okay, we are getting Q plus. Q plus means this is present state it is. So from the previous state, we have got it as 1. So that means we have, when S bar is given as 0, we are going to get the set state. If S bar is 1, then we are going to get the reset state, because this R bar is active now. Okay, so they are all active low inputs, right? So here S bar, it is 0, so we are getting set state. Here R bar is 0, thereby we are getting reset state. When both of them are 1, 1, we'll get the no change condition. You need to have to be very clear with this truth table, thereby we can easily understand this SR flip-flop. Okay. Okay, now let us move on in order to see the SR flip-flop. Okay, so this is our SR flip-flop, right? So this one, it is SR flip-flop. In this SR flip-flop, we have the logic symbol that is being shown like this. So we have two inputs, so which are S and R. We have the third input also, which is the clock signal, and we have two outputs, which are Q and Q bar. And here the symbol, it is almost similar to the SR latch, except for this clock. So if you write enable over here, then it becomes SR latch. If you are writing clock here, it becomes flip flop. That's all. Okay, so here it gives the truth table of the SR flip flop. So for SR flip flop, you could see that here I'll just give you how it is being taught. So here, if the clock is active, see here, for all these combinations, clock is active. So you are going to get the state of the flip-flop. And here what happens is, here clock is inactive, right? If you have not given the clock means then it will not change the state, right? So now we need to have to discuss about these four combinations. Okay, so now I'll show you only one combination of such kind. So first let us take the input as 0 0. Okay, so let us take S as 0 and R as 0. So if we take S as 0 and R as 0, okay, then what happens? So here it is obviously it is 1. Okay, why? Because flip-flop will become active only when clock signal is given. So what happens over here? This is a NAND gate. So you are familiar with the NAND gate. Okay, so what is the truth table of our NAND gate? This is 0 0 0 1 1 0 and 1 1. Okay, so what's the truth table of NAND gate? If any one of the input is 0, output is 1. If all the inputs are same, then the output is 0. Now you look at the truth table of this. Both of them are 0 0. When both of them are 0 0, we are getting S bar as 1 and R bar as 1. Right? So now it is nothing but, so what is this one? It is nothing but RS bar R bar latch now. So our we have already given the clock signal and our inputs are 0 0. So when our inputs are 0 0, we have got the outputs as S bar is equal to 1 and R bar is equal to 1. Right? So in an SR, S bar R bar latch, when our inputs are S bar is equal to 1 and R bar is equal to 1. So what is the state that you are getting? We are getting no change state over there. Okay, this we have already seen in the S bar R bar latch. Okay, so how it is no change state is that here we need to have to start our analysis from 0. We don't have 0 over here. First, let us assume Q as 0 and Q bar as 1, because according to the truth table, according to our concept, our output should be the complement of each other. So thereby we are assuming Q as 0. So now that 0 we are taking it over here. So if any one of the input is 0, output is 1. So that one output will appear over here. So when both the inputs are 1 1, we are getting Q as 0. That means what? Our previous state was 0. Now the present state is also 0. That means there is no change condition that is going to occur. Alright. Okay, so this is what we could say. And here now let us change our input now. Okay, so what will change? We'll change Q as 1 and Q bar as 0. Okay, so we have the input S bar as 1, R bar as 1. This we cannot change because our input is S is equal to 0 and R is equal to 0. When it is passed through the NAND gate, obviously we'll get the complement of that. We have 1 1 now. So now initially we assumed Q as 0 and we started the analysis. So thereby we got it as no change. Now what we'll do is we'll take Q is 1, Q bar as 0. From where we need to have to start the analysis? We have to start the analysis from 0 over here. So when any one of the input is 0, output is 1. Right? So that one appears over here. Okay. So when both the inputs are 1 1, we are going to get the output as 0. What's the meaning of this one? So even if you take Q as 0 or Q as 1, you are getting no change state. Alright. So here we could fill the truth table like that. That means when S is 0 and R is 0, we are getting no change state. So how we are getting no change state, that we have seen over here. So when the inputs S is 0 and R is 0, we'll get S bar as 1 and R bar as 1. And when it, according to the truth table of S bar R bar latch, we are getting no change condition. Even if you assume Q is equal to 0 or Q is equal to 1, you will get the same thing. So that's why we could say that when our inputs are S is equal to 0 and R is equal to 0, we'll get the no change condition. Okay, so that we have seen over here. So now this is how it is been filled. Okay, so first two rows, you could see that clock is active over here. S and R inputs are 0, 0. When S and R inputs are 0, Qn represents the previous state and Qn plus 1 represents the present state. So present state is same as the previous state. When we assume Q as 0, we are getting Q as 0 itself. If Q is 1, we are getting Q as 1. So thereby we could say that when S is 0 and R is 0, we are getting no change state. Right? Okay, now let us move on in order to see the next input. Our next input is S is 0 and R is equal to 1. Okay, here let us take that one. S is 0 and R is 1. Okay. So when S is 0 and R is 1, obviously here we'll have 1, 1 over here. Otherwise, our flip-flop will not work. So now what will be our S bar, R bar inputs that we need to have to see. Okay. So if S is 0, we'll get S bar as 1. If R is 0, we'll get R bar as 0. Is it not? So why it is like that? See, any one of the input is 0, output is 1. Here both the inputs are same, so output is 0. Now, what we need to have to do is how we are getting the output now. So this is again S bar R bar latch. So this is S bar R bar latch. You could see that directly you can tell over here because this is the active one. You will get the output as reset. How we are getting reset, we could prove this one. Okay, so now let us write the NAND gate truth table over here. So our NAND gate truth table is like this: 0, 0, 0, 1, 1, 0 and 1, 1. Okay, so what is the output of NAND gate? It is for first three combinations 1, for the last combination it is 0. Now we need to have to start the analysis from 0. Is it not? Here we have a 0. So irrespective of the other input, we'll get the output as what? Here we'll get Q bar as 1. Right. So that input appears over here. When both the inputs are 1, 1, we'll get Q as 0. That is what I told. If R bar is 0, then we'll get Q as 0. That means if Q is 0, we call that state as reset state. Okay, so this type of analysis that we can do over here. Okay, so here I'll repeat how it is done. We are giving S is 0 and R is equal to 1. Or obviously our clock input it must be 1, then only our flip-flop is active, right? So we'll get S bar as 1 and R bar as 0. So out of these here, this is nothing but our S bar R bar latch. Okay, so according to the truth table of S bar R bar latch, if R bar is 0, then we are going to get the reset condition. How we are going to get the reset condition? We have to start our analysis from 0. So we are starting from this particular NAND gate. Here one of the input is 0, so we'll get the output as 1. So that one appears over here. So both the inputs are 1, 1, so we'll get Q as 0. If we are getting Q as 0, that particular condition, it is called as reset. Okay, so now let us see this one in the truth table. Okay, see here this gives us the second row. So second row is what? We have the reset condition that is being given over here. Okay. So our reset condition, here it is being shown. Okay, so the reset condition is what? This is 0, 0. Even if the previous state is 1, that is going to be reset. That means we are going to get 0. So that's why Qn is called as a previous state. Qn plus 1 is called as the present state. So in the previous state, if Qn was 1, then also it is going to reset. So this particular condition, it is called as the reset condition. That means what? R, we have taken it as 1. R, we took it as 1. So thereby we are going to get the reset condition. Okay, so now let us move on in order to see the next one. So next one is S is equal to 1 and R is equal to 0. So now let us take S is equal to 1 and R is equal to 0. So now let us take S is equal to 1 and R is equal to 0. So if we take S is equal to 1 and R is equal to 0, what happens to our S bar R bar? Yes, what happens to S bar R bar? Our S bar is 0 and R bar is 1. So according to S bar R bar latch, if S bar is 0, we are going to get Q as 1 and Q bar as 0. So this condition, it is called as the set state. Okay, so we are going to get this as the set state because this is nothing but our S bar R bar latch. Okay, so according to the truth table of the S bar R bar latch, if S bar is 0, we are going to get the set state. Right? So how we are going to get the set state? Because if any one of the input is 0, the output is 1 over here. Here what happens? Both the inputs are 1, 1. So thereby we are getting 0. So for S is equal to 1 and R is equal to 0, we are going to get the set state. Here it is. So for S is equal to 1 and R is equal to 0, we are going to get the set state. Right? Okay, now we need to have to see the last one, which is S is equal to 1 and R is equal to 1. Right? Okay, now let us see that particular condition of S is equal to 1 and R is equal to 1. See, when S is equal to 1 and R is equal to 1, what happens is here are clock signal. Okay, both of them are 1 now. Okay, when both the inputs are 1, we'll get S bar as what? We'll get it as 0. Okay, and also we'll get R bar as also 0. Right? So when both of them are 0, then what happens? It will force both the outputs to be set down. This cannot happen in a flip-flop because our outputs must be complement to each other. So thereby we cannot have this particular condition, which is called as the indeterminate state, or it is called as invalid state. Why we are getting this invalid state is because of our inputs S is equal to 1 and R is equal to 1. How we are going to do it? S is equal to 1 and R is equal to 1. Obviously our clock input must be 1, 1. So we'll get S bar as 1, 0 and R bar as 0. So when both the inputs are 0, 0, okay. So when any one of the input is 0, obviously we are supposed to get 1 over here. So here also if any one of the input is 0, we are supposed to get 1. So but according to our definition of flip-flop or it is latch, our outputs must be complement to each other. We are not getting that particular condition. Thereby we call this particular state as the invalid state. Okay, so this is how we are getting the invalid state. So now we'll move on in order to see that particular state in the truth table. Here we have, so here it is. So what is that? Both the inputs are 1, 1. So we are going to get the invalid state. So this is the present state, previous state, which is 0, 1. So this present state, we cannot determine this present state. That's why it is called as the invalid state. Okay, so this table will give you, the truth table will give us enough information regarding SR flip-flop. So how it is done, I've shown it for all the cases. So what we need to have to remember over here is when both the inputs are same, that is when S is equal to R is equal to 0, we are getting no change condition. When S is 0, we are getting reset. When S is 1, we are going to get the set state. When S and R both are equal, we are going to get the invalid state. Okay, so now let us move on in order to see the waveforms so that you will understand it better. So this is a edge trigger device. We have taken 3 clock pulses over here, and this is just a random input that is being taken in order to show how the flip-flop is going to work. Okay, so now the thing is, let us show it with a, whether it is the input is 1 or it is 0, like that. So at edge of the clock, it is a positive edge triggered flip-flop that we have taken. So at the positive edge going, so at this particular instant, what is the input S that is given? So here, according to the waveform that is written, so at this instant, S is 1 and R is 0. Okay. Now let us see at this particular second clock pulse, at this particular instant, what is the input? S input is 0. What about R? R is 1. But there is a change in the S input for a short duration of time, but this will not be noticed because our SR flip-flop will not see to these changes. It will see only during the edge. So at the third clock pulse also, here it will consider the input as 0. Here also our input is 0. Okay, though there is a change over here, flip-flop is not going to change its output because this change, whatever it has occurred, it is in the middle. Okay, so it is in the middle, so thereby it is not going to change the output. All right. Okay, now let us according to this truth table, how this waveform is being written, we need to have to see this is the clock for 3 pulses, clock pulses that is being shown. So at the positive going edge of the first clock pulse, the input S is 1 and R is 0. So when S is 1 and R is 0, we are getting set state. What is the meaning of set state? It is Q is equal to 1. So this is the output. So at this edge, it will raise and we are getting the output 1. Okay, because S is 1 and R is 0, we are going to get the set state. Right. Okay, so now let us see in the second clock pulse what happens. What is the input that is given? S is 0 and R is 1. If R is 1, then it is reset state. So reset means what? From 1 it will come over here. So reset means it is Q is 0. So that's why for the second clock pulse, we are getting this kind of output. So and then for 0, 0, okay, see here it is 0, 0. What is the state of the flip-flop? It is no change. No change means what? 0, that 0 is retained. Okay, so thereby it is retained over here. So that is how we need to have to write the waveforms over here. And it is Q bar is being written. Just complement whatever Q you have got and write down the waveform. So thereby we could represent Q as well as Q bar. Okay, this is the flip-flop that we have discussed. So it is SR flip-flop. So you must be very familiar with the S bar R bar latch truth table because it is constructed using S bar R bar latch. So for SR flip-flop, make sure that when both the inputs are 0, 0, we are getting no change state. If S is 0, we'll get reset. If S is 1, it goes to the set state. When both the inputs are 1, 1, then that particular condition, it is called as invalid state. So these are the 4 different states for the SR flip-flop that we are going to get, provided our clock is active. If the clock is not active, then there is no change condition, or it is the previous state is going to be retained for the present state also, right? That means there is no change in the state of the flip-flop if clock is not given. So only when the clock is given, it will give the output according to the present inputs, as well as it also depends on the previous outputs. It is going to give us the present state. Okay, here in this case, Qn represents the previous state, Qn plus 1 represents the present state. So when the input is 0, 0, we are getting no change state. When input is 0, 1, we will get reset state. That means according to S, you need to have to remember, if S is 0, we'll get reset state. If S is 1, we'll get the set state. When both the inputs are 1, 1, we are going to get the invalid state. So for all these things, make sure that you know the S bar R bar latch. That truth table must be very familiar to you. Thank you, students.